Hello, it's Dr. Bhatt here. Dear friends and students, today the topic is intramolecular aldol condensation. As you find here, it is an aldol condensation which occurs within the same molecule. That's why we say it is intramolecular aldol condensation. Now, how this happens, I'll say that it's not drastically different from the simple aldol condensation which we have already learned. And we have already taken up cross aldol condensation and the simple aldol condensation. The only difference here is that such this condensation, aldol condensation, of course, occurs within the same molecule. A molecule having or a compound having 6 or 7 carbon atoms are most suitable to undergo such aldol condensation, and this chain of carbon atom should have two carbonyl groups, maybe aldehyde group, a ketonic group, or we in general we say as carbonyl group. Now these carbonyl groups present in the same chain of carbon atoms in a compound, one of the carbonyl group acts as an electrophile and the other acts as a nucleophile. Now these electrophile and the nucleophile, they interact together same way as in simple aldol condensation. Now in simple aldol condensation, what happened? An enolate is formed. Here also you get an enolate. The same mechanism is formed. An enolate is formed, and this enolate then takes up the hydrogen atom from the other carbonyl group and forms the final product, which is known as aldol. The conditions of reaction are also same. That is, in presence of dilute sodium hydroxide, which acts as a catalyst, and also other alkalis can also be used, such as sodium alkoxide, but then NaOH is found to be most suitable and has got a catalytic action also. So that gives you the final product, but there is a difference. The most remarkable difference is that since this happens within the same molecule containing two carbonyl group, one acting as a nucleophile and the other acting as an electrophile. So what happens that finally when they combine together, interact together this way, then a ring is formed. We get a loop or ring cyclic compound as a product. And it is noteworthy that the most stable ring cyclic product is obtained in a 5 or 6 carbon membered ring. The other rings can also be formed. Suppose we get a 3-membered ring or 4-membered ring. That is also possible in a compound. But what happens that this shorter cyclic compound containing lessest number of carbon atoms have greater ring strain. There is a strain in 3 carbon membered ring and 4 carbon membered ring, and therefore that is not stable. It doesn't stay longer, and most suitable is 5 or 6 carbon member ring. Suppose the ring contains more than this 6 or 7 carbon membered, and if there are more number of carbon atoms, then what will happen? Of course, the ring strain will be less, but at the same time they will be far away from each other, the carbonyl groups, to interact, and that will not be a stable product which we get. Okay, this is all about molecular aldol condensation, and more of it we go through the examples, and finally we shall have a practice of making out or determining the final product of aldol condensation in a given compound, of course the intramolecular aldol condensation. So it's here. Let us go through. The first example is heptane diol forming 2-hydroxy cyclohexane carbonaldehyde. And as you find, there is a OH group, there is a CHO group present in the compound, and it is cyclic. The details are given here. There is another example where 4-oxopentanol. Of course, there is an aldehydic group, there is a ketonic group, and in presence of dilute NaOH, you get a ring product finally, that is cyclopentuene on. And how it happens is represented here. Same compound, 4-oxopentanol in presence of NaOH, which acts as a catalyst. There is a catalytic action. One of the carbonyl group acts as a nucleophile and other acts as an electrophile, and there is an interaction between the two carbonyl groups serving as an electrophile and the nucleophile, and finally there is a proton transfer. Hydrogen is shifted over here and you get a hydroxy compound, which is aldol product, which on heating forms the final end product having a double bond. So that's why it happens like that. The mechanism is properly explained here. The only thing is you have to find out the electrophile, nucleophile, join them together and take out the hydrogen so that a hydroxy compound is formed. That is known as proton transfer, and you get the final end product. So it's important here. And then another example is 1,4-diketone, or we can call it as 2,4-hexane dione. You get the 2-methyl 2-cyclopentanone, pentanone, it's here. And a very good example is here, that is example 4, where it is 2,6-heptane dione. You find two keto groups here, CO group at position 2 and position 6. Now, what happens here? It is, of course, worthwhile marking that this carbonyl group or even the other carbonyl group both contain, since it is a keto group, there are two alpha hydrogens, alpha carbon atoms and alpha hydrogen atom. So there is a possible interaction between the carbon atom marked here as 1 or the carbon atom marked as 3. So what is we shall go through the reactions and make out the product first with a carbon atom interacting or reacting with the other carbonyl group, that is at 6. So one will serve as an electrophile and the other will serve as a nucleophile. And you get an aldol product here, of course, in presence of sodium hydroxide with a alpha hydrogen at 1. And this aldol product, losing a molecule of water, gives 3-methyl 2-cyclohexanone, hexenone. It's like that a double bond is formed here. Now let us see what will happen when the carbonyl group, the keto group, the alpha hydrogen atom marked at 3 is used as an nucleophile. So it's here. You get the product all right in presence of NaOH. This is with the alpha hydrogen atom marked at 3. And you get a cyclic ring containing 4 carbon atoms. So it is butyl. And finally, on dehydration, you can expect a butynyl ethanol like this, but it is not yielded. This is not the product which we get. Why? Because it's under a greater ring strain and the ring is not stable, as I have already explained earlier. Now, a very interesting talk we have to take up is about practicing. making out the final product of aldol condensation, intramolecular aldol condensation, when 6-oxoheptanol is given. 6-oxoheptanol. There is the oxo group, there is an aldehyde group at 1, oxo group or the ketone group at 6, and 7 carbon atoms are there. So now there are, if you look carefully, you will find that a number of alpha hydrogen atoms are there. And how many alpha hydrogen? At position 2, just by the side of adjacent to the aldehyde group, and at position 6, there are 2 alpha hydrogens, and the ketonic group, oxo group or the ketonic group is here. At position 5, there is alpha hydrogen, and at position 7, there is an alpha hydrogen. So there are 3 possibilities to get the products of intramolecular aldol condensation. Now let us decide, let us determine which will be the most stable product and why. Suppose this alpha hydrogen is used for interaction, then this alpha hydrogen at position 2, C2, can form a 5-membered ring with less reactive. Mark here, less reactive. Keto group is less reactive. So both of them will combine and a 5-membered ring can be formed this way. One serving as an electrophile, the other serving as a nucleophile. Then there is another possibility where the alpha hydrogen at 7, just by the side of the keto group or the oxo position here, a 7-membered ring can be formed with the aldehyde group here and with the alpha hydrogen and the aldehyde group by this alpha product. And there is another alpha hydrogen at position 5. This is just by the side of the carbonyl group or the keto group, and there is an aldehyde group. Alpha hydrogen at C5, this is C5, would form a 5-membered ring with more reactive aldehyde group. Aldehyde group is definitely more reactive as compared to the keto group. So, with more reactive aldehyde group, a chain of carbon atom will be formed and 5-membered ring will be formed. Naturally, we can very easily infer that which will be the stable compound. And since it is a 5-membered ring formed by the interaction of aldehyde group, CO group present in the aldehyde, this will be more stable. And a 5-membered ring will have lesser ring strain. So that's why we can infer that this will be stable. So how to make out the product, which will be the product, what will be the product, and how to make it out, we get here. There are certain steps. We proceed stepwise. The same 6-oxopentanol is there, heptanol is there, and a number of steps have to be followed to make out the product. First step, convert the CO to COH. Here we are using 5th alpha hydrogen at 5th position, and this carbonyl group is to be converted to COH like here, and then link the nucleophile and the electrophile carbon atoms. 2 carbon atoms which has served as an nucleophile and the electrophile have to be joined together, and this way you get a product here which is aldol containing the same carbon atom containing OH and H. Now this OH and H can lose a molecule of water because they are attached to the same carbon atom, and it is quite easily get dehydrated, and you get the final product at step 4. But then this is not stable. For a stable compound, this on big heating forms a double bond and you get one methyl cyclopentanone. Okay, that's all. We stop here and we will be back soon with some other reaction.